Hello friends and welcome at my channel. Today I would like to show you guys how the sine rule is working and why it is working and what are the applications of the sine rule. So let's start. So the idea is in every triangle, so in an arbitrary triangle, we don't ask for any kind of properties. It can be whatever triangle you wish. So this is A, this is B, this is C. The opposite of A is alpha. The opposite of B is beta, and the opposite of C is the angle of gamma. All right, in every triangle, sine of alpha divided by A is equal to sine of beta divided by B is equal to sine of gamma, which is divided by C. So this is the idea, and if you see it for the first time, you're kind of wondering because you say, well, okay, this is working in every triangle, but we define sine and cosine only in right angle triangles. So somehow it's kind of maybe not clear how it is supposed to be working, but the idea is we're just putting a height, let's call it h. This is 90 degrees and this is 90 degrees as well. Well, what is the definition of the sine in this first triangle? Well, the sine of alpha, this is the opposite, which is h, divided by the longest, which is b. Okay. What is the sine of beta in the triangle number 2? This is the opposite, which is h, divided by the longest side, which is a. So what would be the sine of alpha divided over a? Well, that would be h divided by b divided over a, which is a divided by 1, which is h divided by b times 1 divided by a, and that would be h divided over a times b, right? And what is sine of beta divided by b? Well, that would be h divided by a divided over b, which is divided by 1. So we have h divided by a times 1 divided by b, which is h divided over a times b. So they are equal. Well, that's nice. All right, let's move on. So this equation is given. How to prove the second one? Well, in order to prove the second one, we're doing the following. We are producing one more new height, 90 degrees here and there. We call it h1. I hope I'm not kind of overlapping all the ideas here, but it's just a second height which we're producing. And we're having triangle number 3 and triangle number 4. In triangle number 3, what is the sine of gamma? This is the opposite, which is h1, divided by the longest, which is b. And what would be the sine of beta? This is the opposite, which is h1, divided by the longest, which is c. So what is sine of beta divided by b? Well, we had it here, but it was a different triangle. So sine of beta divided by b, with that knowledge, that would be h1 divided by c divided over b, or b divided by 1, which is h1 divided by c times 1 divided by b, which is h1 divided over b times c, right? What would be sine of gamma divided by c? Well, that would be, you see sine of gamma is right here. This is h1 divided by b divided over c divided by 1, which is h1 divided by b times 1 divided by c. This is h1 divided over b times c, which is once again the same. Check. So now we have all what we wanted to prove. Well, that's nice. Why do we use it? Well, imagine you are in medieval ages, okay? And you are trying to measure a distance between A and B. Well, if it's kind of, you can see it. If it's not far away, like 200, 500 meters, you have a rope. You can just take another person holding the rope. You bring some tension to it without looping and so on, and then you can measure it. Perfect. But what about there is maybe something like we have huge problems to get from A to B, like maybe there is a forest in between or some rivers and actually we cannot pass. So what should we do? The idea is the following. Look at this. This is the point A where you are staying. This is the point B where I'm staying. And there is a third person C. And we're making an agreement that this person on a sunny day at 12 o'clock, so at noon, Normally we can see the highest position of the sun, we call it zenith, this is a Arabic word. So the highest position, we are outside, and this person has a mirror in his hand, and he is reflecting the sunlight, okay? We are having spectroscope, and we're trying to measure this angle. So we make sure we're not far away from each other. It's like 200 meters or something, let's imagine, roughly. And the third person is somewhere far away. We don't know exactly how far away, but we're able to measure this angle. Let's call it maybe 89.4 degrees. And let's call this one is 89.6. You know what I'm doing this? Because I want this angle to be 1, so 1 degree. And this person is pretty far away, and there is a huge river between us, so we cannot pass now immediately. And well, we'll make sure this is really straight, so there is kind of exactly 200 meters. We are able to measure it, but this distance is way bigger between B and C, and we cannot measure it physically. It's not possible for us. So that means we are measuring the angles, and now we call it x, and we know that the sine rule is applicable. So look at this. Sine of 89.4 degrees divided over x is the same as sine of 1 degree divided by 200 meters. So we can solve it, we can produce reciprocals. So that means x divided by the sine of 89.4 degrees is equal to 200 meters divided over the sine of 1 degree, right? And what would be the value of x? Well, that would be 200 meters divided over the sine of 1 degree times the sine of 89.4 degrees. We can easily compute it, and this is the distance from B to C. It should be roughly 11.8 kilometers, I think. This is actually one of the things I've done with my students. I'm living in Düsseldorf on a hill, and we were really able to kind of find a possibility to see me with the reflection. Well, maybe I'll show you once in real life. But this is how it was applied until 1974, until the start of GPS. Every map that we are producing in this world is being produced through this principle. It's really crazy, and it's really important. You see once again why trigonometry is important. Maybe I'll show you way more, many more applications of this, but this is one of the most important. So every map that you are holding in your hand, which is elder than let's say 40 or let's say 45 years, is for sure being computed with this kind of application of the sine rule. Isn't that nice? It's crazy. One of the biggest German scientists, or one of the biggest mathematicians in the world in the human history, was Carl Friedrich Gauss. I hope you're familiar with this guy. And he was measuring it himself, and he was doing it so often that this is one of the ideas, these measurements, why he figured out later on so important normal distribution. But let me show that to you. I'm just live checking it on online here. So I go to startpage.com. Startpage.com, and then let's say 10 Deutsche Mark. And now you see the pictures. There you go. This is the nice picture. So this is what we have. And well, you see, this is the old banknote. This is also the same we had previously in Switzerland with Leonhard Euler, also 10. And there is a mathematician, I'm sorry I forgot the name, but the Turkish mathematician is also on 10 lira. So it's nice. There are many other banknotes with mathematicians, but this is very important. And you see, this is the gadget that they were using to measure. This is the curve I told you, which, well, he was inspired by these measurements to produce this curve. And these are the triangles. So through these triangles, they were able to measure the whole distances in the country. And this is one of the, well, most important applications of the sine rule. But prior to Gauss, also in France, Louis XIV was also using Cassini brothers to make the two famous globi, really huge maps of our Earth, and also they produced the sky at the day of the birth of Louis XIV, which is okay. Also nice. You can see it, by the way, in Paris Science Academy. I was able to see it. It's really fantastic, so I highly recommend to do that for you. And well, they also were measuring France. And the joke is Louis XIV told that the map producers took away more land from his kingdom than all the wars put together, because people assumed that actually the countryside is way larger than it happened to be. All right, guys, thanks for watching. I hope you learned something new. See you in the next video. All the best. Bye-bye.